All right, so good morning. So we're going to finish up with coronary artery disease today. The last time we did uh, myocardial performance index, we did LIMP, LIMP, which is left ventricular index of myocardial performance. The other name for that is the TI index. It looks at the overall function of the LV. So not only systolic or diastolic, look at both the systolic and the diastolic function. You have to know how to do that. We talk about the definition. So once you know the definition for LIMP, which is mitral valve opening to mitral valve closing or closure, mitral valve opening, mitral valve closure to mitral valve opening, you're going to subtract the ejection time and you're going to divide by the ejection time. And that worked out to be, this is what it turns out to be. Let's get that. So it's IVRT divided by, IVRT plus IVCT divided by the ejection time. So when you're doing LIMP, when you're doing RIMP, it's a little bit different because you have to do two set of measurements unless you're doing tissue Doppler imaging. If you're doing pulse wave Doppler, then, when you're doing LIMP, this is what you want to see. So it's mitral valve closure. So this is a mitral inflow, mitral valve closure. Then you have your IVCT. Then you have the ejection across the LVOT. And then IVRT, and then opening of the mitral valve. So the definition for LIMP is mitral valve closure to mitral valve opening. You're going to subtract from that the ejection time, and then you're going to divide by the ejection time. And that when you simplify that, it's IVCT plus IVRT divided by ejection time. So you need to review that. We don't do it a lot, but it's a very testable thing. You will get it in tests, and just understanding what it is, is going to help you quite a bit. So if you understand what it is saying, then you don't have to memorize anything, because once you see it, it will come right back. All right, so today we're going to look at DPDT, the change in pressure with respect to time. And we also use DPDT to assess left ventricular contractility. So I want you to conceptualize this. Okay. If you have a normal, so we're going to look at scenarios where you have a normal LV, ejection fraction normal, and then if you have a situation where your LV systolic function is depressed and the heart muscle is weak. So we're going to look at those two situations. So if you have a normal LV, normal ejection fraction, normal contractility, if you have mitral regurgitation, okay, that is blood flowing from the LV across the mitral valve into the left atrium. If you have mitral regurgitation, then if you have normal contractility, that regurgitation is going to occur very, very quickly, because the LV systolic function is normal. And when it contracts, it's going to quickly push blood backwards. The valve may be incompetent. You may have dilatation of the mitral annulus, whatever the mechanism of the mitral regurgitation. If you have a normal LV systolic function, then it's going to quickly, the regurgitation is going to it's going to occur very, very quickly, as opposed to a situation where the LV systolic function is depressed, the heart muscle is weak. That regurgitation is going to take a much longer time, because the heart muscle is not strong enough to force blood across the mitral valve in a quick fashion. And that's all DPDT is. Change in pressure with respect to time. if the LV systolic function is normal, you're going to get that change in pressure very quickly. Okay? So the dPdt is going to be a higher number with a normal LV systolic function because the LV is contracting strongly. Okay? So you're going to get a change. You can generate a pressure in a short period of time, as opposed to a situation where the LV systolic function is depressed, weak heart muscle. It's going to take a much longer time to develop that same amount of pressure. Okay? It's going to take a longer time to develop that same pressure. So your dPdt is going to be less. Okay? So for normal LV systolic function, the dPdt is a higher number. And for a depressed LV systolic function, dPdt is going to be a lower number. And if you remember 1,000, then, so anything greater than 1,000 is normal, and anything less than 1,000 is abnormal. But you need to know how to do it. So again, when we talk about dPdt's change in pressure, that's the pressure developed in the LV cavity with respect to time. Okay, it's an assessment of LV global contractility. The stronger the muscle, the greater the number. So it is the pressure generated in the LV during the IVCT period of contraction. This the isovolumetric contraction time. So it's during this time the pressure generated. Okay, so in order to do this, you need MR, you need to have mitral regurgitation, and you should increase your sweep speed to 100 millimeters per second. So you need to have mitral regurgitation, and then you increase the sweep speed. You're going to use C doubler to do it, and you also have to adjust your velocity to about 4 meters per second. So you don't want to do it. You don't want to adjust the velocity any larger than that. All right. So for the LV, you need to calculate your. Remember, we said during the IVCT period. That is when you're going to look at your dPdt, change in pressure with time. So that usually occurs in the first 3 seconds. So what you're going to do is, we want to look at the IVCT period, which is the first 3 milliseconds. So again, you need to increase your sweep speed 100 millimeters per second. The velocity, you want to at least 4 meters per second. And you want to see the time it's going to take so you get the 1 meter per second interval and the 3 meter per second interval. So when you look at your vertical axis, okay, you're going to see the velocity, and on the horizontal axis is your time. Okay, remember now you're looking at just the mitral regurgitation, I'm going to show you how it's done, but you're gonna the period that you want to look at is the 1 meter per second and the 3 meter per second, and you want to see what time it takes to generate a pressure between the 1 meter and the 3 meter per second. You can do some calculation. So between the 1 meter per second and the 3 meter per second, you want to calculate the pressure gradient, the change in pressure between these two velocities. From the modified Bernoulli equation, we can convert velocity into pressure. So at the 1 meter per second, you calculate the pressure. Pressure is equal to 4v squared. And at the 3 meters per second, you calculate the pressure again. Okay? Pressure is equal to 4v squared using the modified Bernoulli equation. The pressure difference, the difference in pressure between the 1 meter per second and the 3 meter per second It's just a difference in the the pressure, which is going to give you the gradient. The difference in pressure give you the gradient. So this is 32, not 42. So 4 times 3 squared minus 4 times 1 squared, that's a 36, minus 4, that's 32. So this is 32, and it's millimeters mercury. Okay, pressure is in millimeters mercury. And this is how you do it. All right. So the change in pressure is 32, as we have shown before. At 1 meter per second and 3 meters per second, the difference in pressure, the change in pressure, all you do, you use your modified Bernoulli equation, pressure is equal to 4V squared. So the change in pressure is 32 millimeters mercury. And if you divide that by the change in time, then you get your dp dt. And remember what we said, anything greater than 1,000 is normal. So you want to, when you do it on the machine, you just want to see the time it takes to generate this pressure. So it's the pressure generated between the 1 meter per second and the 3 meter per second. This is how you do it. All right, so you need mitral regurgitation. So this is your mitral regurgitation. Everybody know that. It's a systolic flow. So on the vertical axis, you have velocity. On the horizontal axis, you have time. So you just come down to your 1 meter per second. At 1 meter per second, you draw your horizontal line. And where it intersect the MR curve, then that is where the time gonna start, okay? And then you do the same thing at 3 meters per second. You come across where it intersect. You do vertical, and so this is the change in time, okay? So this is if you're gonna do it in the machine, okay? So if you're gonna do it in the machine, this is how you do it. All right, so you have to have mitral regurgitation. Look at this, the cartoon. So the cartoon is right here. Okay, this is your mitral regurgitation. Mitral regurgitation is a systolic phenomenon. Okay, at 1 meter per second, you come across, and then you get the initial time. You go up and you get the time. At 3 meter per second, you come across, and you get the time it's going to take to generate that pressure. The change in time is right here, okay? So all you have to do is divide 32 by this change in time, and you get dp dt, okay? A lot of time, once you put your cursor there, the machine automatically gives you dp dt. Change in pressure with respect to time. You want to look at the IVCT period, and that is why we use the 1 meter and 3 meters per second. But this occurs in the IVCT period. Okay. All right. So again, on the machine at 1 meter per second, you come across where it intersects the graph. You go up and you get the time. 3 meters per second, come across where it intersects the graph. You go up, and that's the time. Okay. The change in time is from the 1 meter per second to the 3 meters per second. And you divide 32 by this change in time, and you get dp dt. dp dt is an assessment of LV systolic function, the contractility. The stronger the heart muscle, the shorter the time, because it's going to take less time to generate the same pressure, as opposed to a weaker muscle. It's going to take a longer time. So when you divide the change in pressure with time, the weaker muscle is going to have a smaller dp dt because of the larger time. Okay, so you have to get that concept. Once you get the concept, you don't have to worry about anything. You can do dp dt for the right ventricle, but instead of using 1 and 3 meters, you use 1 and 2 meters per second. So it is the change in pressure between 1 meter per second and 2 meters per second. And that change in pressure is 12, because, 4 times 2 squared is 16. 4 times 1 squared is 4. The difference is 12. So you're going to divide 12 by the change in time. Okay? All right, so we're going to look at some of the complications of a heart attack. Okay? And we are interested mainly in the mechanical complications. When a patient comes to you with with a heart attack, myocardial infarction, one of the things that you always have to be aware of is what we call cardiogenic shock. And if someone have a heart attack and they presents with cardiogenic shock, there are a number of things that can occur. So you usually don't get cardiogenic shock unless you have more than 40% of the muscle being involved with a heart attack. You have damage to more than 40% of the heart muscle. So the function of the heart as a pump is reduced. Also, you can get cardiogenic shock if you have a ruptured papillary muscle. Okay, so you have wide open mitral regurgitation. So all the blood is going backwards, nothing is going forward. Patient presents with cardiogenic shock. If the muscle ruptures itself, you can have rupture of the muscle, you can have a ventricular septal defect, or you can have rupture of the free wall of the LV. If the patient presents with a right ventricular infarct, then they can also present with cardiogenic shock because blood is now not getting to the left side of the heart. When we talk about cardiogenic shock, we talk about a reduction in the cardiac output. The heart is not pumping properly, or because of some other problem inside the heart, the forward cardiac output is very reduced. Okay? So the patient will be hypotensive because the cardiac output is reduced. The patient will be tachycardic because they're trying to compensate for the reduction in cardiac output. They're going to be cold and clammy, pale. Okay, so remember, RV infarct can also cause it, not only the LV infarct. So LV infarct, if you have more than 40% of the muscle being involved in the heart attack, but RV infarct, because if the right ventricle muscle is damaged, it won't be able to pump blood through the pulmonary circuit in order to get to the left side of the heart. All right, so if you have rupture of the heart muscle and the pericardium sort of seals or prevent the heart from emptying with blood, we call that a pseudoaneurysm. So rupture of the heart muscle, but the heart doesn't empty its blood into the pericardial sac because there is some what we call loculation. It seals the tear in the heart muscle. So you'll get some pericardial effusion, but the patient doesn't exsanguinate and die. So a pseudoaneurysm is a very important one. It's usually result from free wall rupture of the heart muscle. So when you look at it, you'll see a thin myocardium, thin muscle layer. The patient going to have some amount of pericardial effusion, and when you put color flow, you'll see that there's flow into this space. And you can make your diagnosis using contrast, microbubble contrast. But we usually talk about the differentiation between a pseudoaneurysm and a through aneurysm. And one of the differentiating feature is that a pseudoaneurysm has a narrow neck as opposed to a through aneurysm where you have a large neck. Okay, and this is what we so apical four-chamber view. There's a tear in the apex, okay, and there is some pericardial effusion. Blood is in the pericardial sac, but it's loculated. It walls off, so the patient doesn't just bleed out all into the pericardium. So this neck is a narrow neck as compared to a true aneurysm, which have then if you look at the neck, it's large. It's a much wider neck. Okay, so this is a pseudoaneurysm. This is a surgical emergency. Yeah, once you pick it up. Okay, other mechanical complications of a heart attack, you can have rupture of the ventricular septum, so ventricular septal rupture. And when you look at the septum, the area of the rupture will be thin. You put your color fluid there, you have flow across the septum. Usually left to right shunt because the pressure in the LV cavity is larger than the pressure in the RV cavity. You use contrast, either microbubble or saline. Okay, so you have to look for it. Okay, all right. So that that ends our session with.